Have you ever really thought about what happens when something breaks? I mean, not just the loud crash or the bang, but the secret, incredibly violent story that unfolds in less than a blink of an eye. Well, today, we're diving deep into that hidden world, the secret science of how materials actually shatter.
And that right there, that's the big mystery, isn't it? We always see the result, the shattered glass, the dented car. But the entire drama, the real cause of the failure, it all happens in this impossibly small slice of time, the very first microsecond of impact. So let's go there. Let's explore that first microsecond. This is where the battle between force and matter is decided. It's a moment of pure, raw violence that determines whether something is going to hold together or just fly apart into a million pieces.
To really get what's going on, we have to look closer. I mean, much closer than what our eyes can see. We have to go beyond the obvious surface cracks and take a journey deep into the very heart of the material itself. And this journey brings us to the key piece of evidence in this whole investigation, something that scientists call the microstructure. Honestly, you can think of it like finding a unique fingerprint left at the scene of the crime.
So what exactly is it? Well, the microstructure is the unique internal pattern of a material. It's all about how its tiny crystal grains and different internal bits and pieces are arranged. It's basically the invisible architecture that gives a material all of its unique properties.
I love this analogy. Think of the microstructure as a material's DNA. It's this hidden genetic code that basically pre-writes its entire life story, and, most importantly, how it's going to react when it's put under extreme stress. This DNA is what dictates the difference between just bending and completely shattering. So, let's start with our first case study, metals. How do things like steel or copper alloys bleed on the inside when they get hit with a massive force? Well, the answer to that is written deep inside their microstructure.
Now, researchers have pinpointed a few key ways that metals start to fail from the inside out. You've got dynamic fracture, which is basically what it sounds like, cracks just ripping through. But two of the most fascinating and frankly kind of weird mechanisms are something called spallation and another one called twin formation.
Okay, let's break down spallation. Picture this. A shock wave from an impact hits a piece of metal. It travels all the way through it, hits the far side, and then it reflects back like an echo. But here's the crazy part. That returning wave isn't a compression wave anymore. It's a tension wave. It literally starts pulling the material apart from within. So the material isn't breaking from the outside in. It's being ripped apart from the inside out.
And then you've got twin formation. And if you thought that last one was strange, get ready. This is just wild. Under incredible instantaneous pressure, whole sections of the metal's crystal structure will just flip. They instantly reorganize themselves into a perfect mirror image of the original structure. It's like a desperate last-ditch effort by the material to absorb a ton of energy and try to resist breaking.
All right, so that's how metals can fail. Now let's shift gears to something a little more complex, composites. Think carbon fiber. See, unlike metals, which tend to fail in a fairly uniform way, composites break in this chaotic, cascading chain reaction of events. And you can see the difference so clearly right here. On the one hand, a metal might bend, it'll deform, and then it'll tear. It's kind of predictable. But a composite, on the other hand, oh man, it can fail all at once, in a layered catastrophe. It's not one single break, but a whole bunch of smaller failures happening almost at the exact same time.
And here's that cascade in action. It's a total domino effect. First, the resin that's holding everything together, that's called the matrix, it starts to crack. Then, the fibers start to pull away from that resin, which is called debonding. Next, the really strong fibers themselves begin to snap under the load. And finally, the layers of the composite literally peel apart from each other. That's called delamination. It's game over.
So, we've got all these microscopic clues: spallation, twinning, matrix cracking. We've got the evidence. But here's the biggest challenge facing scientists today: connecting these tiny clues to the final large-scale crime of catastrophic failure.
This quote from the research just hits the nail on the head. It says scientists can see all this microscopic damage, and they can measure the big macroscopic outcome, like a loss of strength. But drawing a direct, predictive line between those two things, that is incredibly difficult.
This table really illustrates that great divide. We can see all the clues on the left, but how do they actually connect to the final outcomes on the right?
For instance, how many microscopic twin boundaries does it take to cause a specific measurable drop in a material's strength? Or how dense do microcracks have to get before the whole structure just fails? Answering these questions is the key to everything.
And that is no exaggeration. Being able to look at a material's microstructure and predict exactly how and when it will fail, that really is the Holy Grail. It would completely revolutionize how we design everything, from airplanes and body armor to bridges and buildings. Which of course leaves us with one last, really fascinating question to think about. If we could finally crack this code, if we could bridge that gap between the micro and the macro, just imagine for a second. What new, seemingly impossible materials could we finally design and build? What does the future of unbreakable really truly look like?